Yes.
And if people can turn off their microphones and maybe even their video just to help the broadband, that'd be great.
Yes, that's great. Yes, as Betty was saying, really, you know, my great friend Matthew, I'm sure Matthew would have been watching this, and we talked endlessly about caves. You know, I, as many people do, miss him sort of terribly. I think is terrible, great loss, you know, to the geological and caving community. So really, this is another tribute to Matthew. And really, what I'm going to talk about is actually really why caves are important, because they can actually tell us something about the landscapes. They are not just kind of holes in the ground. They actually hold those holes, places where the rock has gone, actually can tell us quite a lot about how the landscape has actually developed over time. Oh, where is it not? Aha, there we go. Now, a lot of rocks, to my mind, are made by the wrong sort of rock. They're made of silicate rocks, sandstones, basalts. These are some sort of familiar ones at the bottom and some less familiar ones at the top. These are silicate landscapes, and they tend to be dissected by surface drainage, by rivers, just kind of cutting down through them. So the rocks are not really very soluble. And one of the problems with those is that we could say, well, these landscapes, of course, the landscape is a very dynamic thing anyway. It's kind of changing all the time. But the general form of the landscape shows, you know, how old is that? It's difficult to actually determine from these silicate rocks. One way we can do it is you look at sediment deposits. Sediment deposits are a record of erosion of older rocks. And this is just a sort of stream, sort of gully cutting down through these older rocks, and essentially the gravel and sort of sand that is at the bottom of this sort of pile is going to be the first bits that have been eroded out of this gully, and the stuff that's on top that you can see sort of here is going to be the last bit. So it's almost like in a sort of stratigraphy, recording how the land, that particular little bit of the landscape has changed. And if you find mammoth tooth or a piece of wood that you can carbon date within these layers, you can perhaps get a chronology which helps to tell you how long this feature has actually taken to form. But the problem with these sorts of things is they are actually themselves vulnerable to erosion, because you can see the stream here is actually cutting down through the older gravel, so they are likely to be destroyed. But actually, we use these quite a lot, particularly in southern part of England, and these are called sort of river terraces. And as a river kind of cuts down into its bed over time, it leaves behind sort of little platforms. You never see a continuous long terrace along river, little sort of patches of the old riverbed which might have a bit of sediment on. And this is the River Severn, which is not far from where I grew up. And you can see there's a sort of house built on a sort of terrace here. And this is the kind of the present sort of floodplain. And then there are other terraces further up. And this is almost like an idealized cross-section through the Severn terraces. And like I say, you never find all of these in one place, but the older ones are going to be actually up here, and successively younger ones further down as the river cuts down into its bed. And with the fossils in them particularly, so if you find hippos in it, it must be 125,000 years ago. They help to sort of give us an age or a date for how the landscape has evolved, and how, in this case, the River Severn has actually cut down into its landscape. So the important thing also I should mention here is the difference between what I call relative dating and absolute dating. Relative dating was you can say this is older than that, and that is older than that, and so on. Those are relative. We don't actually know how old they are unless we find something that can give us an idea of what the age actually is. And then there's absolute dating, and there's no such thing really as absolute dating unless you find sort of something scrawled on a rock, you know, Ice Age ended 19th of July, I think was the date. So I'll talk a little bit about those in a little bit later. It's not absolute dating, it's dating that gives us a number, but it's based on a particular technique that we're using. But the problem with these river terraces, they're great if you have them, but glaciation, which Ireland has suffered or benefited from, depending whether you're a glaciologist or not, Ireland has experienced a lot of glaciation, and that can erase river terraces and modify the channels and pretty drastically modify the landscape. So it can be very difficult to actually work out what has been going on before the last glaciation, because glaciers are like giant bulldozers. They plow across the landscape, bulldozing all in their paths. So they really muck things up. It's difficult to work out, you know, how the landscape has evolved and how long these things have taken. But a much superior rock, of course, is limestone, and limestone landscapes are characterized by underground drainage. They're, rather than having surface drainage, they are dissected by underground channels. And the reason for that, of course, is that limestone is weakly soluble in rainwater, which is, of course, slightly acidic. And so rainwater percolating down fractures within the rock can gradually enlarge those. And eventually, some of them may become large enough for people to explore. Of course, we call these caves. Once you can explore them, you can start interrogating them to try and find out, well, what are they telling us about how this particular landscape has actually developed over time? And well, why are caves the best for this? There's 5 main points, really. The underground drainage is bound to be linked to the evolution of the surface landscape. So you've got streams coming from an impermeable rock, draining onto the limestone and sinking underground. And if that impermeable rock is eroded away or eroded back, so that sinkhole will move elsewhere. So the underground drainage is responding to changes in the surface landscape. And secondly, caves have roofs on them, you see. So they're bedrock channels. Oh yeah, they're bedrock channels. So often you get the earlier roots are actually preserved reasonably intact. Whereas in surface rivers, quite often the river will actually destroy its older channels. As I say, as roof conduits, they've got the roof on. So they preserve a history of these channels right from the very beginning to the stage where they're abandoned and even eventually will be destroyed as the surface lowers to intercept them. Then fourthly, they form a pretty effective trap for sediment, mud, sand, gravel or whatever, and also animals that either fall into them or are washed into them or wander into them by mistake. And lastly, caves and the things they contain, they're protected from surface weathering and erosion, which are factors that really count against finding fossil bones like bits of hyena on the surface because of the weathering and erosion, whereas caves protect these things from that. So in essence, there are 2 main things. Caves preserve evidence of changing drainage patterns through time, and also the stuff within the passages, either formed in situ or introduced from outside, is actually preserved from damage for far longer than anything on the surface. So that's why caves are so good. And really, in essence, they combine aspects of a leaky bucket. We can work by looking at a cave system, we can sort of work out roughly, well, where did the water go in at particular times? Where did it come out? Because water within a cave system, which is an underground drainage system, it will tend to sort of appear at the lowest point that the limestone is exposed. So by examining a cave system in detail, you can actually work out, you know, where the various holes were within the limestone that the water came out at various times. So it's a bit like a leaky bucket. And also because things last much, much longer in caves because they're protected from weathering and erosion, it's a bit like the back of the sofa. You find all sorts of things in caves which you thought were lost. So like bits of hyena in Castlepoot Cave, it's the only place we find them in Ireland where quite clearly they were out and about on the surface, no evidence of them except in the caves. So what I'm going to do now actually is go through some caves, some getting increasingly complex to show you what we can do with some very, very simple observations. And this is a simple cave system. And what we look at, there's effectively 2 zones within the rock. And one is called the Phreatic or saturated zone. And it's called that because all the passages are completely flooded. It's below the water table. So you can see on this section, you see all the passages are completely flooded. So if you're going to be exploring these, you need to go into cave diving, which is really only for people who are completely mad. And in these passages, you actually find that because they're water filled, they dissolve the limestone in all directions to produce elliptical or circular passages. And this is one actually in Peak District in Derbyshire. And you see the water originally has been percolating along a bedding plane, you can see here, and it's dissolved the roof upwards and it's dissolved the floor downwards to produce these fantastic phreatic tubes. So you see a circular passage like that in a cave, and you know that at some point that was in the Phreatic zone. But clearly this one isn't, because this guy is not a diver. But above the water table, in the what's called the Vigo zone, the passages are largely water air filled, but they've got streams actually just flowing along the floor like this and going over sort of cascades and things eventually till they will reach the water table. And because the water is just flowing along the floor of the passage, not the roof, you get these kind of canyon-like passages, tall slot-like passages, and there's a characteristic Vigo Cave passages. And here we've got a sinkhole. This is the Cooler River sink on the Boreen. So the water's coming off the shale and it's going to hit in the limestone. It's disappearing underground, such as here. And this is where some of the water sort of comes out. This is, I think, this is called Blue Lady Cave in somewhere up in the northwest of England. So those are the main sort of passage types. You've got these tall, thin Vigo passages, and you've got the circular phreatic tubes. But of course, the landscape changes and that affects the cave. So this is, again, our simple sort of cave. At an earlier time, this impermeable catchment rock, which might be shale if you're in the Boreen, perhaps would have extended out to here, and that was where the water was sinking. But because it's retreated, this sinkhole has been abandoned and now is just sort of dry. And again, the valley will have cut, the stream will have cut down into the valley, and an older resurgence or rising where the water used to come out will become abandoned, and the water now finds a route to a lower point on the limestone. And quite often within a cave, you will find these keyhole shaped passages. And this is one in a cave in South Wales. And you can see it's got a circular bit, which is obviously a phreatic tube. And you can see this one's originally formed along this joint here. That's the thing that has transmitted the water very early on in the cave development. Then a phreatic tube has developed, and then the water table has fallen for some reason, because the river has found a lower point, or water's found a lower point to come out, and you get a Vigo trench carved into the floor. And there are real examples. This is actually one on the Boreen. This is a beautiful cave called Ioe Cave. This is me in my youth in 1986. This is actually one of these keyhole passages, though you wouldn't really know because it's so cluttered up with all these stalactites and stalagmites. But this is bits up here is the old sort of elliptical phreatic tube, and then it's got a Vigo trench carved in the floor. And this is another fine bit of passage with some beautiful scalloping. I'll talk a little bit about that later. And this is the far end. This is one of these kind of old waterfalls, but it's completely dry. Because what's happened is that now the water, it sinks at various points along the shale edge. This is the edge of the shale, sinks into the stream, trundles all the way down this meandering stream, and then it gets diverted off down a quite steep sort of cascade. And that's where all the water goes. And the original route now is completely dry. So what's happened is the water has found a lower point to get out, and you end up with this abandoned stream passage. So that's a fairly simple cave on the Boreen. Now I'm going to say a little bit about chronologies. Where do you get the numbers from? How old can we find out, how old are these cave passages? How long have they taken to form? And this is one actually in California, Crystal Cave. And it's rather conveniently, it's a little block of marble sandwiched between schist and quartzite, which are insoluble rocks. And there's a place called Yucca Creek there, another one called Cascade Creek. And the water from Yucca Creek is leaking through the marble to Cascade Creek. And it's been doing that for a long time. So when you look at it in section, you've got a whole series of passages. And the relative chronology, we know must be, these are the oldest ones, the highest ones. And then as these streams have cut down to their beds, so you get progressively lower and lower stream passages until you get to the current active passage there. And this is one of these relic passages, which is actually a show cave. So that's a relative chronology. We know which passages are oldest and we know which are the most recent ones. But what we really want to do is actually find a way of dating it, get some numbers. And these are the absolute chronologies, which I say are not absolute, really. They're just, they depend on the technique you use. And this is one radiometric dating. And what you're dating is these things called speleothems, which is stalactites and stalagmites. And they contain, quite often, the water that they grow from effectively contains small amounts of uranium. And that gets trapped within the crystal structure and then it decays to thorium. And you can measure the difference between the uranium thorium, and it can give you a date going back perhaps as much as 500,000 years. But one of the problems is, of course, these things, as they grow, they're going to bury the older bits. So quite often it can be difficult to actually find bits that are really, really old. And I don't know if you noticed, there's somebody looking at you just down there. Anyway, so you go along to this cave and you collect samples from each of the different levels, and you would expect these to be the oldest, next oldest, and this down to be the youngest. So let's actually have a look and see what happens. Ah, yes. You see, we've got one date down here, which is older than any others, but it's at a relatively low level. And right up at the top, we've got dates which are not really very old at all. And as I was saying, this is one of the problems, is that quite often these stalagmite layers will tend to cover up the older stalagmite layers. So it can be difficult to actually find a sample that is actually really, really old without actually doing some quite serious destruction, which people might balk at the idea of smashing up styles just to get a date. So it's not a perfect solution. It's a good solution if you can find the styles or stalagmites, but very often it doesn't give you a particularly good date. So we can try something else. Another absolute chronology, which is nowhere near as precise, but it gives you an idea of the dates. And this is using paleomagnetic dating, because Earth's magnetic field has flipped from normal to reverse and back to normal. And even within those normal phases, the kind of orientation of the magnetic field has actually fluctuated. So by carefully analyzing very fine-grained sediments, mud and silt within these things, the mineral grains within these, if they contain a bit of iron, they will sometimes, in very still water, they will, or still mud like we've got down here, they will actually line up according to the Earth's magnetic field. So, but with some quite fancy kind of jiggery-pokery, you can actually get an idea of the Earth's magnetic field orientation from these samples. And that can help you to figure out, well, what age are these things? And in fact, this comes out quite a lot better. You know, you've got things in the right sort of order, but again, you've got quite a spread in these sorts of dates. You know, it's not precise at all. So we could try something else maybe, and this is what's called cosmogenic dating. And this is where, if you've got quartz pebbles sitting out in the sunshine out in Yucca Creek, and all the time they are out exposed to sunlight, daylight as it were, they will also be exposed to cosmic rays. And cosmic rays are incredibly high energy particles. And if they hit an atom of a particular element within these quartz pebbles, a silicon atom, we'll say, because there's a lot of silicon in quartz, they can convert it to, say, something like aluminium 26, and that has a half-life of about 720,000 years. And the longer it's out there, the more aluminium 26 builds up. It's still tiny, tiny amounts. And then once they get carried into the stream, carries them into the cave, that aluminium 26 starts to decay to magnesium 26, and you can measure the amount of these two elements. And that gives you an idea of how long it has been cut off from daylight. And because it's got a long half-life, you can go back several million years. And in fact, what you do is you collect pebbles from these various things, and here we've got dates. And they've got quite big sort of error bars. Again, it's not a precise sort of thing at all. You're talking about error bars spanning 200,000-300,000 years, but it's giving you the right sort of sequence. The oldest passage at the top, the younger ones at the bottom. So that's three methods of getting an absolute chronology, none of which give you an actual absolute number. So it's a way of actually getting an idea of how old landscape is, the sort of timescales that it's been evolving on. Now, that was something much worse. A hideously complex cave. This is a place called Ogof Drynan in South Wales, which was only discovered in 1994, and it now has more than 70 kilometres of passages. And it is quite clear that we're nowhere near the limits of what it actually ultimately contains. And there's probably 150, 200 kilometres of passages in this cave. A kind of an awesome place, and I had almost 40 trips down this back in the mid-90s trying to work out what is going on. You look at that and you think, oh my goodness, it's an absolute maze of passages. Really, really difficult, you would think, to figure out what's going on. But the thing is, you don't look at it all as one thing and think, oh my goodness, it's like trying to eat an elephant You do it a small piece at a time. You don't eat the whole elephant in one go. And so that's what you do with this. And so a very good friend of mine, Andy Farrant, and I, we had between us, we had about 80 trips down there actually working out what was going on, doing a little bit, going to particular bits of the system to work out what was actually happening there. And the things we were looking at, the key observations, which I've sort of mentioned early on with this very simple cave, we want to know what is the altitude of the water table when that passage was formed. And so this is a keyhole passage. This is a sort of elliptical phreatic tube in here, and then it's got a Vadose trench carved into it. So if we know what the altitude of this is, we know that the water table must be above this, you see. So that's really, really useful. So we want to know, is it in the phreatic or the Vadose in this particular passage? Then the second thing we've got is flow directions. What direction was the water flowing? And you think, oh, how can you tell that? Well, it's actually very, very easy. And it involves my favorite cave features of all. I'm not a stowel person at all. What I love most are these big scoops here. These are called scallops. And these are solutional features. They're caused by eddies as the water's flowing along. Irregularities were called eddies in the water, and they dissolve out these scoop-shaped features. And you can see them in the roof there, little ones there, and more little ones along there. And these tell you what direction the water's flowing because they tend to be steeper on the upstream side and more gentle on the downstream side. They're asymmetric. And so they can tell you, in this case, the water was flowing into the picture, away from us here. And also they give us an idea of how fast the water is flowing. Bigger scallops indicate slower flow than smaller scallops. So when these were forming, the water was flowing fairly slowly. And then the passage actually filled up quite a lot with sediment. And so we had all the water just sort of barreling along this tube up here. And then Vadose, the water table's fallen as streams washed out a lot of the sediment and carved a trench in the floor. So flow direction is really, really important from the scallops in the passage and also sediments. And these are some current ripples that were found in one of the passages I'll say a little bit about in a minute. And they're asymmetric. They're steep on the downstream side and gentle on the upstream side. So they tell us quite clearly the water's flowing that way, going sort of into the picture as well. So flow direction is very important. And then the third thing really is cross-cutting relationships. And as good geologists, you will always realize that's very important to know, to figure out which rock is older than another one. If this dike cuts that sill, and we can work out what came first, what came second, and so on and so forth. So cross-cutting relationships of passages is really important aspect of it. And the thing that really, as cavers, we really want is a high-quality survey. And Andy Farrant and I were involved in quite a lot of the surveying, well, a tiny amount of the surveying, but quite a few surveying trips of this enormous cave system. And even when the things aren't that great, this is actually down a squalid little sort of passage, you see, and I am what they call the surveyor's dog. I'm on the end of the tape measure, and this is a guy called Mike Reed who's got the compass and the clinometer to work out which direction the passage is going and whether it's going up or down or whatever. And from that, you can actually put together a survey, and you've got actually altitudes on the floor, 307 meters, 317, 301, amazingly detailed. And this is really important to actually figure out what's going on. If you just had these lines without all the numbers on telling the altitudes, you wouldn't be able to figure out what's going on. And that takes us to an initial assumption we made when the first survey came out with not really very much data on it. Where did the water flow? We now know that the water is draining from various passages. This little squiggly arrow there, and it kind of comes down here, and it goes along there, and then it turns quite sharply, and it heads off down the main streamway. And this is the main streamway. The first time I ever went down there, actually, on a photographic trip with somebody else. But and it goes off down there, and it doesn't reappear at the surface. The water doesn't reappear at the surface for another 8 or 9 kilometers. And there's a big passage coming in from the north, and so there was just an assumption, oh, well, and it doesn't have really much water in it at all now. It's just a little tiny trickle, you see. So the assumption was that this was an old tributary passage that has now been abandoned. So, it seemed very reasonable. And then there was the discovery of these ripples, which were found just here, and they indicated that water was actually flowing northwards in this passage, and that completely changes all our thinking about how this cave had formed, and it really meant, right, we've got to look at all the different bits to figure out what's going on. And it turns out the actual flow direction, this passage was flowing northwards along there. And in fact, it's very obvious when you're there in the passage, the roof stays at the same height all the way up there, but the roof height here is a good 5 or 6 meters lower. It's like a hole has been punched in the wall of this and it's captured the flow of the water southwards. So this passage formed later. So that's one of the things, is never make assumptions just based on looking at the plan, the map, as it were. You need to actually go and look at the thing in reality, as it were. So what I'm going to do is actually quickly go through how we worked out what was going on, because this horrible mess of passages is a compilation of many different drainage routes. Think of each one of these as being like a river or a stream that's flowing from kind of almost source, where the water goes in, to sort of outlet where it actually comes out again. And so, where were they flowing? There were 3 valleys today. This is the current sort of situation. There's the Usk Valley, which has a huge river, the River Usk, over to the east. There's the River Clydach to the north with the Clydach Gorge, and then there's the Afan Lurid going down here. And this is where the water comes out for the cave now. You can see it's a long way that we haven't yet found between these two. And the limestone dips gently about 10 degrees to the southwest, which is almost parallel to these passages. So over time, what's going to happen is these underground rivers are actually going to find a route further down dip. So the whole system over time, all these passages, we would expect this is the most recent one and it's got the stream in it, and these are going to be older. But where did they go to? And so we go right back, we're winding right back to almost to the beginning of the whole system. And at that time, we don't know exactly when that was, most of the limestone was actually covered by younger sandstones. And there's really only a couple of places where the water could get in. And you've got to have a point where water could get in, and then you've got to have a point where the limestone is exposed at a lower altitude for the water to get out. You've got to have a slope, a gradient within the aquifer, otherwise the water's not going to go anywhere. And it turns out that you had a sink up here, and this corresponds to very, very old passages that are about more than 380 meters altitude today. And then we think it sort of came out at another little bit of limestone that was exposed a little bit lower, perhaps about, well, maybe kind of 380, 370, maybe even 400. There may be higher associates. So this is the oldest one. It went in at the Clydach Gorge, came out at the Usk Valley. And this is a long time ago. And to give you an idea of the scale of landscape change, this is a place I went to a few times, and I would just stand there in awe of how the landscape changed, because I'm standing up here at roughly the sort of level that original swallet or sinkhole where the River Clydach sank into that ancient part of Ogof Drynan. And you can see there's the village of Clydach down there, almost 1,000 feet below. So in that time, since the Ogof Drynan system first started developing, you've had more than 300 meters of downcutting, more than 1,000 feet. It really kind of, you think, oh my goodness, that is a lot. That's a lot of erosion. This cave must be quite old, but how old? Anyway, going on a bit, as I say, the water's always going to want to come out at the lowest point that the limestone is exposed. Remember this valley here, originally it was entirely on the sandstone, but eventually the river is going to kind of erode through the sandstone and punch a hole into the limestone underneath. And as soon as that happens, that becomes a more favorable route for the water to take. So it abandons this route and it heads off there. And so that's what you get. You can see there's a whole series of very zigzaggy passages and nasty kind of maze-like passages heading off towards water coming out here. And these passages going this way were quite nice and big. And some of these were really kind of tight and rather squalid. And what it's telling you is that the water can't go equally in all directions through the limestone. So these joints were quite big open joints. It could easily go that way. But if it wanted to sort of go southwards, much more of a struggle. These joints were sort of much tighter. And so it's kind of zigzagging all over the place. And it's got all these, horrendous little maze passages. So it's more of a struggle for the water to actually go this way. But it still managed it. So that's where it got directed southwards. But meanwhile, the River Clydach has been cutting into its bed as well. So I can play at that game. So the limestone then becomes exposed at a lower point than either here or in the Lewid Valley. So at that point, everything reverses. And what you actually get this, more limestone exposed up here, lots of little streams sinking here, sinking into this thing, and the water is now draining to the River Clydach. And in fact, some of the water from this river is actually then going the other way, is going northwards. And that's what we saw in those sand ripples indicating northward flow. So all of a sudden, the whole system has turned almost through 180 degrees. It's like a seesaw. It was flowing south, and now it's flowing northwards. But remember, all the time, this valley is going to be getting deeper and deeper and exposing more and more of the limestone. And that's what happens. Eventually, the Lewid Valley wins out. It gets down to a lower point than anywhere else on the limestone, and that's it. Thenceforth, you've got a little bit of drainage sort of still going that way, but the vast majority of the water actually continues sort of southwards. So it's a hydrological seesaw where, depending on where the lowest bit of limestone was, that is where most of the water would go. And today, that's what happens. You've got little trickles going that way, sort of relic, there's a little kind of spring there. And this is where the big springs are. There's a couple of them there. So that's the modern system. So that's how you work out what to do with a horrendously complicated system. Oh, this is me back in 1995, my first trip down there. This streamway, cavers like stomping along big streamways, but this one just went on and on and on, and you think, when's it going to end? It was about 2.5 kilometers, and then you've got to come back. So great days those. And this is looking at the surface. So we've looked at these cave passages, and you've worked out how the cave system has changed through time, and that can then be kind of translated to some extent into what's happened on the surface. So this is the Clydach Valley up here, and we know that you've had more than 300 meters of downcutting in this area since the cave first formed. And this is the Usk Valley, which is a very old feature, been there for a long time. Then there's a huge kind of embayment in the scarp here called Cwm Llanrhynarth, and we know that that's more than 650 meters that this scarp has retreated since the cave first formed, to the extent that you've lost several hundred meters of cave across this bit, which is a terrible shame. There's a big passage underneath the Bloinge here, and there's a continuation underneath Gilwan Hill here, and there's a huge chunk being removed. So it's telling you we've lost a lot of scarp there. So it tells you the scarp isn't retreating all at the same rate. And here you've got the Bloinge, perhaps 100 meters of the scarp retreat. And then further to the west, you've got the Lewid Valley, and we can work out there's been up to about 80 meters of downcutting since the cave sort of first since the valley first intercepted the limestone and influenced cave development. So hopefully it gives you an idea. If you've got a really complicated cave, you can actually work out quite a lot about the landscape from that. But it requires a lot of effort, a lot of trips, some of which were very, very long, 14, 15-hour trips. And what we would really like is the timescale. And amazingly, this guy called Chris Smith, and for his PhD, he actually analysed some of these stalagmites that myself and Andy and various others actually collected from various parts of the system. And you can see the elevation here, the very high passages up in the 380, 400 meters, think of War of the Worlds. You're talking about sort of dates getting close to 1 million years. And in fact, there are some more dates that Chris has had since then, which are about 1.2 million. Then you've got others which are, quite a bit younger. So even the modern streamway, the one that's still active, is 120,000 years at least that it forms. So it's a very, very old system. And this, the dates we get from here are actually using their radiometric dates, looking at the decay of uranium into lead, which can take you back much further than uranium thorium, take you back millions of years. So lots still to be done there to work out what's going on, but I'm perhaps getting a bit old to be going down on some of these 14-hour trips. So what I'm going to do is actually look a little bit at some Irish examples now, and the Boreen is a place I've been to many times, and I've scratched my head a lot about it in County Clare. And most caves in the Boreen form at the shale edge, and these kind of paler grey areas, these are the edge of the shale that sits on top of the Carboniferous limestone, you see. And most of the caves formed by streams sinking off the shale, hit the limestone, and they sink underground, and most of them actually drain southwards, because that's the general dip of the limestone is at a couple of degrees to the south. And we've already talked about Ioe Cave, and this is actually one of them, which is actually, it does flow south and then it decides to go north for reasons known only to itself, but most of them drain south. But away from these still existing shale edges, you would expect to see other old shale edge caves formed when the shale edge was further out. And we don't, we actually see very, very few caves away from the shale edge, which suggests that for a long time, most of the Boreen was actually covered by shale. So water couldn't really get in to the limestone underneath. It's effectively a seal on top of it. And then glaciation stripped away the shale so quickly, there was almost no time for significant shale edge caves to form further out. But I'm going to talk about 3 caves here that are particularly interesting because they're a bit anomalous. There's one called Pollinate, which is also sometimes called Doolin's Stalactite Cave, little thing here. Ioe Cave, which is the most famous of the show caves there, and then another one called a Vigo Cave, which is right down in the southeast, which is rather a collector's item really, but a fascinating place. So Pollinate is a large part of it is actually a classic Boreen cave. It's got a little stream like this that's flows off the shale edge and it hits the limestone and it flows along this little sort of rather squalid streamway. It's much easier now because they've actually excavated it to make it bigger, so people can just walk in. You just have to crawl along this. And then it suddenly pops out into this big chamber, and then it disappears off down another sort of rather tight sort of passage down there. And there's other big kind of chambers up here, which are actually mostly filled with mud. It looks big, but it's actually only about 3 feet high. But the key feature in Pollinate is this amazing stalactite, which some people call the soggy dishcloth. so no laughing. No. Yes, it is. Anyway, the soggy dishcloth. And so the thing is that what's going on here, you know, you've got this rather squalid, scrofulous little cave popping out into something bigger. And the thing is, don't be distracted by the soggy dishcloth. That's what everybody goes to see. And they miss the really, really interesting aspects of this cave. And it's very much a case of, look at the thing, and it's behind you. The interesting things are behind you. And one of them is this little sort of at the sort of bottom of the stairs, sort of roughly where they are, just opposite. You can see there's this kind of little sort of alcove here, and you can see it cuts up into the next bed of limestone there. And here you've got, this is where the stream today sort of trundles off down there, and it really gets quite tight and squalid. But you've got this big kind of domey sort of area here, something going on. And then in the roof near here, you've got this kind of almost looks like a bell, you know, a limestone bell, and it's called a Cupella. And all of these features are evidence that water was actually being forced into this chamber when it was self-water filled under pressure. So these are pressure inlets, basically water squirting into a vast water-filled chamber. And these are coming from the wrong direction, really. These are mostly coming from the south and west, rather than from the north and east, which is where the current streamway is coming. And you can also perhaps see here, you've got enormous great scoops. These are actually giant scallops, like a meter or two across, indicating that water was moving very slowly northwards in this cave. And here's some more of these cupolas, these kind of bell hole-like things. And the soggy dishcloth is actually rooted in one of those. And this stalactite has actually formed since the cave has drained, because stalactites only form in air-filled passages, really. They don't really form in water-filled passages. So they tell us that, yeah, this is a much later addition. It's just fancy decorations, frankly. But so when you look at these, you see here these kind of alcoves. This is the water is squirting in from these various places and also squirting in from over here. And these are these sort of pressure inlets. There's quite a few of them, actually, and they are all indicating that water is coming in from the west and from the south, and it's moving northwards, which is completely contrary to the current drainage sort of systems within the Burren, and it suggests that something odd is going on. The water is actually sinking somewhere over to the west and then being diverted to some considerable depth before coming back up. A bit like a U-bend under the sink or the toilet. This is the the upflowing bit of it, as it were, but quite enigmatic. Now I'm going to go on to sort of Ioe Cave, which is another great enigma. And of course, there's Ioe Cave, otherwise known as the very dark caves of Father Ted fame. This is the survey. You know, it's a good few hundred meters long. You've got the entrance here, and you've got scallops. They're really very, very faint. I have stared at the roof of Ioe Cave on many occasions looking for scallops, and they are not very conspicuous at all. But what there are indicate that water was actually flowing into the cave when this passage, this phreatic tube, you can see there's a big phreatic tube here, and now it's got a vadose trench sort of underneath it, you see, in a current active streamway. So the scallops indicate it's flowing inwards, but the present streamway actually flows outwards from this bit, which is completely flooded. And when it really rains, it continues all the way along there, and it'll pour out the entrance, not quite through the gift shop, but so that's a bit odd. And also there's a stalagmite date from round about here of 440,000 years ago. So that tells us that this cave was already partly drained. It was in the vadose zone, you know, close to 500,000 years ago. And my suspicion is that in fact, the water now goes this way, but is diverted along there because there's another passage that would have gone off here that is now blocked. So we need to get more cavers digging there, and that would explain why the scallops going in. So that's a tributary. This is a tributary going to a much bigger passage, and I'm not the only one who's stared at this area quite a bit, hoping to find inspiration and a way on. And to put it in context, Ioe Cave, it's a phreatic tube, so it formed below the water table, yet it's perched high above the valley floor. This is the Ballyvaughan Valley, and Ioe Cave is like 60, 70 meters above. So almost certainly the valley was here, but at a much sort of shallower level when Ioe Cave was forming. So it's giving us an idea of perhaps what the landscape looked like more than 500,000, perhaps 1 million years ago. The general features were there, but everything was not as deep as it was now. And Vigo Cave right down in the southeast. This is a place called Loch Inchquin. Vigo Cave is almost right at the top of the limestone. This is the shale on top, you see, so that's an impermeable catchment for streams. And for a long time, it was thought that Vigo Cave could be an abandoned sink. So streams flowing off the shale would sink into the limestone and then drain southwards along Vigo Cave to who knows where. And this was one of the big questions, puzzles about cave as well. Where did Vigo Cave go? Worth a dig, as Cave has often said. But when the first time I went there, which was, oh goodness, probably more than 20 years ago actually, and it looks a bit like a sort of vadose canyon, formed in the vadose zone. But the thing is that at the far end, where it says dig, that's a description and an instruction to cavers. There are these big kind of scoopy sort of like things, and you can see the limestone's highly polished. And it was immediately obvious to me what was happening here, that water was coming up from this bit here under pressure. And as it came up, it was fluidizing the sand. There's a lot of sand down here, which quite a few cavers have spent a lot of time digging this sand out. It's fluidizing the sand, and the sand was polishing the limestone. And here's another one of these inlets where water's been squirting into the passage when this entire passage was water filled. So it's not a sinkhole at all. It's an ancient resurgence. It's somewhere where the water was actually coming out from a cave somewhere else. So you still have the question, where was it coming from? Rather than where was it going, where was this water actually coming from when this cave formed? And it's obviously pretty old, but there's not really much in the way of stalagmites, stalactites or anything to date it with. You could potentially do something with the mud, but nobody's done that yet. So what might we be able to do? This is a very general attempt to sort of figure out what the Boreen might have looked like. This is the Boreen today. This is the shale edge, as it were, and all the rest of it is limestone. And most of the caves around the shale edge. But if you wind back maybe 2 million years, who knows? We don't have dates really on this. Ioe Cave, I suspect, may have been draining from one valley to another. Probably the other way, actually. I got my arrow the wrong way around here. But more significantly, there's a place called Carron, which there's a delightful pub, it's called now actually, that overlooks the Turlock. It's the highest Turlock in Ireland. And at some point in the past, it would have been a big hole through the shale cover onto the limestone underneath. So streams draining off this shale would have sunk in the limestone. And I think they were draining southwards and then they were coming out at Vigo Cave. The shale edge across much of the Boreen has actually retreated a long way in places, so you end up with these little bits. But where Vigo Cave is hardly moved at all. So going back to this idea that the escarpments don't all retreat at the same rate. Some bits will go back much faster than others. So wind forward perhaps a million years, Ioe Cave lies abandoned, might be a little bit shale left on the hill. But what's happened with the stream that's flowing from the Carron depression, all the water flowing there that used to flow to Vigo Cave, this river that we see here has continued to cut down into its bed, and it's truncated this route, and the water now comes out at a place called Fergus Risings, Fergus River Cave. So we can get a general idea of how the landscape has evolved. Fergus is now the present outlet for the Carron water, but perhaps Vigo Cave was when the valley was perhaps 30 meters higher, 30 meters or more higher than it is now. So these are just very preliminary. You know, it would be so good to have some actual really good dates off some of the things there, but not yet. So now coming close to home for those of you down in Cork, I'm going to talk about a couple of places. One that I worked on a long time ago and one I've been thinking about really very, very recently. This is actually a map from a forthcoming book on the caves of Munster and South Leinster, or some similar title, produced by University of Bristol Speleological Society, and it'll probably be out towards the end of this year, probably early next year. All the dots are caves, and there are also these circles, and these are patches of old sediment. And so O means a Oligocene, so that's kind of 30 million years old. And the question mark means, oh, don't know what's only there. The question mark indicates that we know it must be quite old. It's kind of Cenozoic in age, but we don't know quite how old it is. So first talk about Balletgiblin Quarry, which is one of these Oligocene sites. And it looks like this, and it was Mike Philcox that drew my attention to it. He said, you should go down there. There's a fissure there and it's full of mud that's definitely not Pleistocene. And I went there and this is what I saw, a kind of great mass of bright red sediment within these kind of fissures. Fascinating place. Kept me occupied for years, scratching my head about it. What it actually represents, when you actually go and look at it in detail, which I did, you can't go in there now, apparently. Some store for explosives, apparently, on the site. Anyway, and it turns out that it's actually part of what we call a Phreatic Loop. So it's a phreatic passage that loops down one joint set and up another joint set, and then it actually does it again. A bit like the U-bend under the sink, really. And then it's been filled with this red and yellow sort of sediment. And one of the things, after carrying bags of this stuff around for years, I managed to get somebody to look at it, and they said, oh yes, the pollen from this is a Oligocene, so it's 30 million years old. This is a cave that was operating 30 million years ago, and there's still a bit of it preserved in the Irish landscape. So this is really a classic bit of behind the sofa type geology. We wouldn't expect to sort of find this, but it's been preserved deep beneath the surface. And so these are very old caves, and it's a very old landscape. This is the present land surface. You've got mudstones off to the north, Carboniferous limestone, and this is the River Blackwater off to the south. There's a big spring quite near here called Two Neave Spring, which disgorges vast amounts of water. Balletgiblin Quarry here. But we can extrapolate because we know Balletgiblin Quarry is part of one of these loops of a phreatic passage. And these don't, in Ireland, tend to sort of go much below about 100 meters below the surface. So if we say this is, 100, no more than 100 meters, we can say that perhaps the valley floor has been lowered by about 100 meters in 30 million years. So you've lost most of the cave, but you've actually got this little bit. And there's another quarry nearby called Cupella Quarry, which has another piece of this ancient system. And we know from the direction from the scallops in this cave that it was flowing towards where the black water is now. So I would call it a paleo black water, which is perhaps a little bit closer. So the valley floor has been lowered by 100 meters in 30 million years, but almost certainly the landscape look pretty much the same, perhaps not such nicely tended fields and rather fewer white bungalows, but it's not changed. The major kind of hill masses were where they are, and the major valleys were where they are, and they've been there for tens of millions of years. Now, if you've got, this tells us that the landscape and the limestone is being exposed for tens of millions of years, and that puts a real problem on, well, how old are some of these other old caves, the ones that are now abandoned by any sort of stream? Are these really old or not? And this brings us to the Mitchelstown caves, and there's a series of three. There's the Mitchelstown New Cave, the Show Cave. There's a place called the Old Desmond Cave, which is the old Mitchelstown Cave. And then there's another one a little bit further to this called Pollinate, I think it's called. Fantastic photos by Rob Mulroney, and they're essentially rifts and big collapsed chambers in dipping limestone. You see the limestone dipping here, and lots and lots and lots of boulders and things. And you can see these kind of rifts and then big chambers developed kind of on the bedding planes. But how old are they? For a long time, I just sort of glibly said, oh, well, they must be millions of years old. They're completely out of equilibrium with the present landscape. The present surface drainage has completely abandoned them, so they must be very old. So I thought, well, perhaps they're, 5, 10, 20 million years old. Who knows? Just a wild guess. But because of this book that I'm involved in, it got me thinking a bit more about it. And these fantastic pictures, again by Rob Mulroney, give a clue to what's going on. And that's a lot of the passages, these big passages, don't really have any significant sort of scalloping on them. And they're rifts that have been kind of dissolved out by almost static water. And then you've had water going along the bedding planes, dissolving those out and undermining the beds of limestone, causing these big collapsed chambers. But a few of the passages, and this is the main passage in the Desmond passage, got these beautiful, very, very, conspicuous scalloping. And you can see the scalloping here. The water is kind of hammering through this, that sort of phreatic tube there. So these are main conduits. The water is actually kind of going quite fast through these, but then in these, it's hardly moving at all. And that's giving us an idea of what's happening, is that water's hammering into these, but it can't continue to sort of flow on. There's something resisting the flow, and the water is then forced in all directions along the bedding planes and along joints and things. And each time this happens, each time you get a big flood bringing water down here, it dissolves a bit more of the limestone along these joints and along the bedding planes and creates these maze caves, as they're called. And they now lie at the foot of the Galtee Mountains, somewhere in here. I'm not sure exactly where. You can tell where the limestone is because it's beautifully green. And as soon as you go to the old red sandstone, it's not as green. This is the three caves. There's a Polskahina, Desmond, and Mitchelstown, and you can see this kind of maze-like pattern to them with these kind of major conduits that bring water in. But they're now isolated from the present stream. They're about 20 meters above the present stream. But I think actually what's happening, these streams probably have not wildly changed their course in the last couple of 100,000 years or so. They will tend to be coming off at roughly the same sort of point. And I think this stream was probably originally draining into these caves. And these, I think, are what's called floodwater maze caves, where there is resistance to flow. The water can't just flow straight through. Remember I was saying in Argolf Drynen is that certain directions the water struggle to get through, and I think something is blocking the water getting through very easily, probably because the limestone is dipping quite steeply, And if you've got a thick shale band somewhere within that, that will actually act as a blockage and really restrict the flow of water through. And then you look at, this is a cave called Skull Cave in Albany County, New York. And I think this kind of really epitomizes what was happening in the Mitchellstown caves all those years ago, when they were still being fed by a stream coming off the Galtee Mountains. You've got a sinking stream here, and you've got another one up here, and the water sort of comes down here. It says to spring, partly blocked by resistant strata. And I think that's what's happening here. There's probably a thick shale bed or chert band that's stopping the water actually getting through. And when that happens, all the water just sort of backs up, and then it flows down, and it etches out, it dissolves out joints and long bedding planes. The same thing here, sinking stream here, goes down there, water struggles to get out, and so it just fills up this passage, and then it kind of flows all the way and it joins that one. So I think that what Mitchellstown caves are these floodwater maze caves, and they're not anywhere near as ancient as I thought. They're probably no more than a few 100,000 years old at most. But again, it's one of these things, it'd be great to sort of actually go there in person. It'd be great to get some actual dates, though how one would do that, I don't know, because there's so many beautiful stalagmites and things in the Mitchellstown caves. I think people would not be wanting me to smash them up, and all the old bits got to be somewhere at the bottom. So I'm going to finish there anyway and just say that I'm not expecting, I mean, caves are quite hostile environments to a lot of people, and I can understand why. I've been in some quite unpleasant situations underground. But there's a few show caves, and you can go around to those, and you can actually make observations. In some cases, nobody has really noticed before. So like in Pollinate, nobody seemed to have noticed these kind of pressure tubes before. And the thing to look for when you're going down Ioe Cave or the Mitchellstown caves or whatever is, are the passages phreatic or vadose? Is it circular like here, or has it got a sort of canyon or slot-like form? So this is one of these classic keyhole-shaped passages. Then you can look at the scallops, what direction are the scallops going? These are going into the picture, and what size are they? These are relatively small, so the water was really kind of hammering through this phreatic tube when it was being formed. And you can also look at the sediments. As good geologists, of course, you'll always look at the sediments and think, oh, that's gravel. That, the sediment particle size tells you something about flow velocity, and you've got cross beds and ripples and all sorts of things. And then as good geologists, you will always look for cross-cutting relationships. Which bit came first, which bit came later. And then it always helps if you've got a good survey. And I would hope that, well, some of the, with this book that I've been involved in, one of the things that came up the other day was saying, well, actually the main Mitchellstown survey is close to 100 years since it was done. It's about time we did a new survey, because that would give us an awful lot more data, and that would actually help us to understand what's going on in those absolutely fascinating caves. So anyway, I'll stop there. I think I've been going on for quite a while, and happy to answer any questions. All right, thank you. Right.